Hello, in this lesson, we're going to talk about the continuity, i.e., what is the concept of a function is continuous at A? So that's our question. Recall our definition of limit, right? Definition of limit says, suppose f of x is defined when x is near the number A. This means that f is defined on an open interval that contains A, and it says except possibly at A itself. So as a matter of fact, when we consider limit at A, we do not concern whether the function is defined at A or not. If it's defined at A, fine. If it's not defined at A, we can still consider the limit of the function at A, but because we only need to observe the behavior of the function near A or in the neighborhood of A. So we can make the value, if we can make the value of the function arbitrarily close to L, as close as possible, by restricting X to be sufficiently close to A on either side of A, but not at A. Okay, not at A itself. All right, this was the definition of limit. As we recall, the key point in this definition, not only that we want the function to be as close as to a limit, if that limit should exist, but also that whether the function is defined at that point does not matter to the existence of the limit. So now we are introducing the definition of a continuous function at A, and this is the statement. Definition: a function is continuous at A, at a number A, I would say, or at an input A, if the limit of the function when x approaches A, f of x, is the same as the function's value at A. So here's the picture. You can see we not only consider the limit of the function at A, which is, defined by the intuitive definition we just talked about, but we also concerned with the definition of the function at A, that particular point. So this is obviously a more requirement than just have a limit at A. So from this picture, we can see as x getting closer and closer to A, the function's value is getting closer and closer to f of A. So the former capital L, which has capital L, has become, in the case of limit, is turning into an actual function value. Okay, so this is a more requirement than the limit. So from this definition, we have three items we like to mention. Okay, the first one is that the function must be defined. So the first one is f of A must exist. Okay, f of A must be defined. So unlike in the limit case, whether the function is defined at A or not, it doesn't matter. because we only concern the function value in the neighborhood of A, maybe, except A. So A is not included in the consideration of evaluating the limit. Number two, the second, okay? The second says the limit must exist. This limited requirement, so this must exist. Must exist. What does it mean a limit exists, right? We haven't studied the limiting, if the limit exists, right? Limit from left is equals to the limit from right. So for that requirement, it also implies the limit from left of A, right? So I'm going to put a little symbol on the shoulder from left and limit from right. Both exist and they're equal. Okay, so that was quoting the theorem that we have in the section we study limit. Number three. So number three says, well, that equal, right? So limit from left, limit from right, they both exist and equal. And of course, then that makes the limit of the function at A. And thirdly, these in item number one and in item number two, these two items must be equal. Okay, so must be, I'm going to change it to is defined. Okay, so it's much gentler. Okay, so the definition of continuous function at a point is actually has a stronger requirement, and there are actually three requirements. And now the next question is, what is the opposite of continuous function, right? So naturally we ask, what is the opposite of, right? What is the opposite of a function is continuous at A? Right? What is the opposite of this statement? So quite naturally, we ask that question. Well, from the definition's perspective, right? From definition's perspective, and we have dissect the condition that is required for a continuous function, right? Then it will be the opposite of the three conditions, right? So be the opposite. So here are the cases, right? If I call the first one A and second one B, and this third one C, okay, I like to give you an insight from the logical standpoint, right? So for a function f to be continuous at A, meaning A, B, C, all must be satisfied. A, B, C, all must be satisfied, right? So A, that means A and B, okay, and B and C. They all must be satisfied. So all three must be true. Now, the opposite, which is not continuous, would be the not, okay? Not, let me find the symbol. I think this is the symbol. Okay, that's the not. But that equals to not A or not B. Okay, listen carefully the word I use. Or not B. Sorry. Not B. Not A or not B or not C. Not C. This relationship is a generalogical relationship. Okay, the opposite of A and B and C, which is the bar, indicate the opposite of A and B and C, right? So these are read as and, right? And the union, which is mean or, right? The opposite of A and B and C is A or B or C. So this or relationship will tell us that there will be many cases for not continuous. Okay, so using this logic as now as our starting point, and we're going to analyze both continuous and not continuous. Okay, so not continuous. So from the definition, we can tell, right? When you read the text, when you read the definition, this is the place we need to spend the most time. Not only examine the definition itself, we also need to think if this is what is the opposite of is not. And typically, the is not part is often tested, right? Because it encourages us to study deeper. All right, so with that consideration, right, we have not A. What is not A? Well, f of A is not defined, okay? So the cases, right, opposite of f is continuous at A. The first case, case number one, is that f of A is not defined. Okay, well, and we also say f is not defined at A. So that's the opposite for not A. Not B. Okay, not B. Not B will be more interesting because for B, we have multiple cases, right? The limit, which is the limit does not exist because not B means the limit does not exist. The limit does not exist and we have multiple cases. It could be this one of them does not exist, right? It could be one of them does not exist. Let me write one of the two does not exist. One of, we use or, right? We don't need both does not exist. We just need one of them does not exist. It could be that the limit from left does not exist. And then this will not be true. And this will not be true. It could be the limit from right does not exist. And therefore, this will not be true, and that would not be true. Right? So that's two cases by itself. Secondly, right, so I'm going to put a smaller cases. In case 2, we have, say, lowercase a. And secondly, it could be both exist. Okay, it could be both exist. Both of limit from left and limit from right exists. But they're not equal. Okay, so the opposite of that, it could be that, right? They both exist but not equal. They both exist but not equal, then this limit does not exist. And what else case could there be? Well, for infinite limit, those are not just, they also considered not exist. Okay. So second case, actually there are three other cases. And case number 3, okay, the big case number 3. Oops. Oh, let me bring this down. Case number 3, right, the big item. The opposite of C, right, the opposite of C. That, which means the limit from left and right exists, right? And the limit exists, and the function is defined, right? The function is defined, but they're just not equal. If that happens, it's not continuous, right? So when we bisect, it's made clear what are the cases for discontinuity. So we have the definition of a continuous function at a point A, and we also have, the 3, 4, 5 cases. There's, it can be more cases if, we consider infinite limit. Okay, because in the case of infinite limit, it's not continuous. All right. So now we got the 3 major cases, 3, 4 cases of discontinuous. So let's look at some examples. Number 1, we got this graph. Right? We have 3 points of concern at 1, at 3, and at 5. So let's look at these 3 points. What's going on here? Right, from the graph. So let's look at, okay, try to keep everything in the same graph. Okay, so you see everything. So what we're gonna do, we're gonna still use this table form, right? So let's look at 1. It looks like the limit from left and limit from right exist, but we're not concerned with that because the first thing that get to our attention is that f is not defined at 1. So the first condition is not satisfied, right? If you look at the 3 conditions, right, the first condition is not satisfied. So I'm going to bring these three conditions right here. All right, so now we have everything on one screen. Right? So it's not defined like one. We need to go further. No, we don't need to. So we can draw the conclusion, right? We can draw the conclusion. And then we can say F, oops, F is not continuous at one. You're done. If anybody asks a question about continuity at one, we're finished. At three, right? At three, at the point three, what kind of situation we have? It's defined as three, right? F of, the first condition is second condition, limit from left and limit from right, they both exist, but not equal, right? So we check the first condition, we check A, right? F of three is defined. F of three is defined. Secondly, we check continuity. So what happened is both exist. So we have this situation. They both exist, but not the same. So this situation applied here. Oops. Okay, so maybe I should not do this. Okay, sorry. The screen is only so big because if I make it smaller, you're not going to see the sign on the shoulder. So I'm just going to consider, I'm going to write case 2, case 2, lowercase b. Okay, that should do it. And by this point, do we need to continue to check the third condition? Do we need to check this condition? No, no need. So we can draw the conclusion to say F is not continuous at 3, right? So at a certain point, you only have to check one of the condition is not true. But you go down the list. You do go down the list. So you have something to follow, right? So let's look at point 5. At point 5, right? At point 5, you can see F is defined. It is defined. And B is what? Limit exists, right? Limit exists. No problem, right? If you look, you can limit from left, limit from right, they both exist. And C, so this is the case you have to go down all three, right? Because otherwise you cannot say, so this is approaching 3, and you need to mention all three. So the last case is that obviously the limit is not the same as the value of the function at 5. Okay, so what we have here is case number 3. Case number 3, right? In our case, it's 3. It's 5. Sorry, 5. Right. So this picture covers all 3 cases, but we actually have more cases. Okay, limit from left, and we can see in sometimes these cases could come up. All right, so that's first example. So let's look at some other examples. Okay, let's look at some other examples. Example number 2. Okay, here we have 3 examples. Okay. You could graph it, but you don't have to. Okay. In the first function, right? The first function. First function, as we see, obviously the domain does not include 2. Okay, domain is x not equals to 2. And the question is asking us, where are each of the following functions discontinuous? Well, this is a rational function. Rational function, right? It has limits everywhere in its domain, right? We have that in our limit definition, and it's also a simply substitution. So let's look at for any function, right? We say for any x not equals to 2. For any x not equals to, obviously at those points, f is defined at all of those points, right? So f of x is defined, right? And those limits, if we consider those limits, right? Limit as x approaching any one of them, right? For any a not equals to 2. And we consider those limits, right? It's just going to be the limit of the function, right? Replace it. We're going to factor, right? We're going to factor the top will be factored to x minus 2 times x plus 1. So since x is not 2, since a is not 2, right? A is not 2. We mentioned that we're observing limit of the function at every point in the domain. Okay, so that's why we take a is not 2. X minus 2 is reduced because a is not 2. So in the end, the limit would just be limit of the function of x plus 1. So in the end, it's just going to be a plus 1. Right? So we have the situation, we come to the situation that for this function, right? This given function, and this latter function are equal everywhere except x is not equals to, for x is not equals to 2, everywhere in the domain. We have a theorem, right? We have a theorem that these functions is the same everywhere, then the limit will not be the limit will be the same everywhere but this point, right? So, and since the latter function is continuous everywhere, and therefore this function is continuous everywhere except 2. right? So for this, since we are to answer this question, if where the function is not continuous, so obviously the function is not continuous at 2. Okay, is not continuous at 2. The reason is f is not defined at 2. So f is not defined at 2. So the first reason, right? The first reason. So the first reason is violated. So I'm going to put this next to us, right? So the first reason. So we don't need to check further. Okay, we actually don't need to check further. Then you say, do I need to check all of these? Well, you want to confirm that, but really at 2, but you also need to have some insight because they want you to indicate those points that are not defined, right? Where are each of only not continuous? Okay, so that's the second one. Let's look at the second one. The second one, you know what? We can have a picture I'll just show you the picture for this function for last. Okay, so this function, if you graphed it, right? Graphing will help us to see better because I didn't mention some of the features on the graph. The point I was making here, right? At 2, the function is not defined. So the software doesn't give us that. So we need to put there. So it's not defined there. It's not defined there, right? But it's defined everywhere else. It's defined everywhere else. So that's the graph of the function. So what I illustrated here for not 2, right? Everywhere else there's limit, and the limit is the same as the function's value. Okay. So that is true. That is true, right? So that is true. Therefore, the only point that is not continuous is true. So the first case. Let's look at the second example. The second example, we don't have definition problem, right? If you look at the domain, right, it's almost the same function. The second one, it gives us a definition, right? So if you use that picture, right? If we use that picture, so at 2, it gave us a definition, right? So f of 2, right? For f of 2, it told us f of 2 is equals to 1. So even though this is circle, right? So we can put f of 2 equals 1 as our definition. 2, 1, and that's a black dot right there. So as soon as we see this, we know what is the problem, right? We knew what the problem because we analyzed our situation. Okay, so I'm going to put this as, it's not necessary, but just to make the point. So it's just tell the reader that I know is defined at 2, but it is not the limit of the function. So in this case, the first condition, right? So let me make the picture just a little bit smaller so we can have everything in one screen. right? All right. So you can see the first condition is checked. Second condition is also checked, right? Limit from left, limit from right, the same. But the last condition is not satisfied when we check it, right? So you can go that way too, because the limit is not the same as the function's value at that point. So that's number two. That's number two. Okay. So how do we say it? Okay, so let's say it. Let's say it with words. Okay. I think let me write it down the words so that you know how to express it. Okay, so this is what you're gonna say. Okay, so here you're gonna say number one. So you can go by the items if you want, right? So f of 2 is 1, right? B, you can say the limit exists. The limit does exist, right? For our particular function, but x approaching 2, so you need to change that. This limit exists, okay? C, then you're going to mention the limit, okay? What is the limit? The limit as x approaching 2, what is it? So you need to tell the reader what it is, right? Well, we can borrow the work we did earlier, right? We can borrow the work we did earlier. So you're going to show this piece of work. So that's equal, and that's 2. So that's 2, and that's 2. So then you direct substitution. So that's 2 plus 1, that's 3. That's 3. Okay. Thirdly, so number 3, when you mention that this limit, okay, you're going to mention 3, right? The limit is 3, not equals to, is not equals to f of 2. So this will be, you're basically quoting the definition, in the definition. So this will be the most proper way to express it. Okay, of course you can have a separate line to do that. Okay, so this is how we express it. This is how we express it. Okay. So we did a B, and of course we have C. Okay, just before we do C, I want to introduce the concept of removable discontinuity. Discontinuity. What is removable discontinuity? Right? If you look at the first two, A, right, the first one, right, the first example, the function is discontinuous just at one point, right? So how can we make it continuous? Can we make it continuous? And the answer is yes, right? B is trying to, because we know the only problem is that the function is not defined at 2. Therefore, we say maybe we can do something, right, to remove that discontinuity. So how about, right, we defined a function because we know the only problem is a definition. So instead of defining that at point 2 equals to 1, we define it as 3. Now the function in A is continuous. How do we know that? Because if the only point is 2 is the point of discontinuity, and we're going to assign the value, right? So 3 is basically the value, as we can see this time and time again, right? Where did we wrote that? Okay, for B. Yeah, for B. Yeah. For B, we've got it, right? So we got the limit. We quote that part, right? The limit at 2 is 3. So we just take that 3 to define the function value at 2 to be 3. And now, by this time, all 3 conditions are satisfied. So as a result, this function, which is redefined, is continuous at 2 now. In fact, f is now continuous, everywhere, because we already demonstrated it's continuous everywhere but 2. Now we make it continuous at 2, so now the function is continuous everywhere. Okay, so this kind of discontinuity called a removable discontinuity. Okay, sometimes it can be done, sometimes may not be done. Okay, now, so let's look at the third example, C. C. Okay, it's defined as 0, right? In fact, it's defined everywhere. So is it continuous, right? So for not equals to 0, we have 1 over x squared. So it's continuous everywhere except maybe at 0, right? So let's see what's the limit of the function at 0. So the first condition is checked, right? So A is checked, right? So f of 0 is defined. So f of 0 is equals to 1, defined. Wonderful. Number 2, we're going to check the limit, right? So we're going to take limit of the function at 0. So what do we get here, right? The limit of the function as x approaching 0 from either side, okay? From less than 0, greater than 0, from larger than 0, smaller than 0. Do we need to separate? No, we don't need to. You could, but we don't need to. Because x squared, right? If a negative number is going to turn into positive. So this is going to be positive infinity. Does not exist. Okay, in this case, right? It's an infinite limit. It's infinite limit. So when we do the C, obviously they're not the same, right? So obviously this is not the same. If your function is defined, it's equals to a finite number. It's not going to equal to infinity. So these two are not the same. Not the same. So this function is discontinuous at 0. Discontinuous at 0. This function is discontinuous at 0. So if we look at the graph, right? So we can graph it. Let me see if it will do it for us automatically, or I need to do some manual work. That's okay. There we go. Obviously, I need to add some work. Okay, so this is the picture. This is the picture. All right. And at 0 equals to 1. So I'm going to add that point to define the point. And I want you to think of, is it removable discontinuity? Right, so let me make a little adjustment to the picture. Well, the curve is consistently positive. So this is the curve. Okay, we can remove that because we have that function over there. We obviously have a discontinuity, but is this discontinuity removable? Yes, you're right. This discontinuity is not removable discontinuity. Not a removable discontinuity. Okay, so in these three examples, we have seen that there are discontinuities that cannot be removed. All right, so let's look at another example. The other example is example number 3. This function is very special. This function is very special. We call it the largest integer function. And this function is written as 2 bars, okay? And x is in between double bars on both sides. How is this function defined? Well, this function is defined is for any input, the output is the largest integer that is less than or equal to x. Okay, let's see a couple examples. If my input is 0.9, the largest integer that is less than or equal to 0.9, less than or equal to 0.9, obviously is 0, right? So for 0.9, the output is 0. And for this, by the same token, you can see if you go interval by interval, if it's 0.5, it's going to be 0, right? So every number between 0 to as close as possible to 1 is 0, right? Until you have 1. And that limit equals to, that output is equals to 1. So that's why you see this in the interval between 0 to 1, all the other numbers, their output is 0, but the output for 1 is 1. There's a jump. In the interval between 1 to 2, right, between 1 to 2, if you talk about 1.1, 1.2, 1.3, right, so if we talk about 1.1, that the largest integer that's less than or equal to x, that's going to be 1. So you keep going, right? We keep going until we have 1.9. And that integer, that output is also 1, right? And as we keep going until we get 2, right? You can have 1.999, it's still 1. Okay, so until you have 2, and the output is going to be 2. So that's why in this interval you have this jump of 2. So this is the function in our consideration. Okay, so let's look at the point of discontinuity, right? So what are the points where are the continuities? Discontinuities. Okay, I put plural because I can see, as you see this picture, you know there are a lot of discontinuities, and there are also lots of points of continuities. So let's look at the continuities, right? Say on this interval, starting from this interval, okay, between -1 to 0, all these are continuous except at 0. So discontinuity at 0, right? Continuity at 1, discontinuity at 2. So we're going to take 1 point as the example. Okay, so observing the function's behavior, observing continuity at 1. Right? Is the function defined? Is the function defined? I'm going to put f of x, right? Obviously, at 1, f of 1 is equals to 1, right? F of 1 is equals to 1. It's defined. Okay, let's look at limit. At 1, let's look at limit. Okay, I don't need to write this. The limit of the function at 1, f of x. F of x, limit at 1. When we try to observe the limit, right, at 1, approaching 1 smaller, approaching 1 from larger, we encounter different rules. So this is the case that we're gonna have to consider limit from left and limit from right. You guys follow me? Okay. So not in every case you do left limit, right limit. Okay. Sometimes it's not necessary, like in earlier example, 1 over x squared. You don't need to do left limit, right limit, because they're going to end up to be the same. Excuse me. So we only do limit from left or limit from right, usually, absolutely, out of necessity. Okay, so in this case, we are going to consider limit from left smaller than 1, right? And what would that be? That's going to be 0, right? Because we're approaching 2, we're approaching 1 from smaller than 1. Anything smaller than 1, the function value will be 0, right? And then we observe limit from right of 1. So I'm going to put the positive sign on the shoulder. In this case, obviously, it's 1. So the second condition, so these two, right? So what do we see? We see that limit from left exists, limit from right exists, but they're not equal. They're not equal. If they're not equal, that means what? That means the limit of the function does not exist, right? So that means the function at 1 does not exist. The limit of the function at 1 does not exist. At this point, do we need to check further? No, we don't need to check further. We're just making the case, right? The first condition is satisfied. Second condition is not satisfied. And we don't need to go ahead and check the third condition. That's what I meant. Okay, so no need to check the third condition. We can just draw the conclusion. And then you say the function, the function f of x is not continuous at 1. Similarly, okay, for every integer, we're going to do the same, right? So our conclusion is that the function is not continuous at any integer. But continuous okay, sorry, but continuous at all non-integer. Or continuous everywhere else. That's done. All right. All right. So we've done enough examples and applying definition for continuity and continuity, right? And limit from, and next concept would be continuous from left, continuous from right. And we already mentioned that. So, but here, what does it mean continuous from left, continuous from right? Okay, I also mentioned we're going to take a second look of the example we just did, right? Where's my cursor? Right there. Okay. All right. So what does it mean continuous from the right of the number, continuous from the left of the number? For example, if the limit from right is equals to function value, it is continuous from right. And we have a situation like this, right? In this case, right, we know that the two limit does not exist. The two limit exists but not equal. But this limit, right, in this case, the function when we take limit from right, it is equal to f of 1, right? So in the example of, okay, in example number 3, the limit from right, okay, I want you guys to see that's a plus sign there. Can you see? Yeah, I'm sure you can see. It is equal to, so this function, even though it's not continuous at 1, it is continuous from the right of 1. Okay, that's what you say. So you say f of x is continuous from the right of 1. All right, so that's how you say it. You basically quote the definition. You really just quote the definition and replace it with the number of your interests. Continuous from left is similar, but do we have continuous from the left? No, there's no continuity from the left. But you can also say, right, it is not equals to, so this one, you can say, since this is not equals to f of 1, which is equals to 1, right? And you can say f of x is, I'll kind of copy and paste to save time. F is not continuous from the left of 1. All right, so those are the wordings we can use. That's the second look. Next, we're going to introduce another definition, which is this definition is about what does it mean a function is continuous on a interval. Can't find my cursor. Where is my cursor? There. Okay, there we go. What does it mean a function is continuous on an interval? So this is the question. This is our question. Well, this is a definition. If it is continuous at every point in the interval, and in parentheses it says if f is only defined on one side of an endpoint of the interval, we understand that the continuous, sorry, the typo, at the endpoint to mean continuous from the right or continuous from the left. Okay, to illustrate this, before we do the example number 4, right? So so these are the cases. These are the cases. If we say a function is continuous on an interval, right? And the interval could be like this, a comma b. This kind of interval we call open interval. So in open interval does not include a, does not include b themselves. So it is just f is continuous. So in this case, f is continuous for every x, right? And this x is between a and b, not including a, not including b. But what if you have an interval like the following? Okay, it's not open, it's half open. Okay, it's half open. So I'm going to give you an interval that is half open. There. So what does that mean? Well, in this case, that not only f is continuous in every point at a and between a and b, but also including b, right? Because b is included. In this case, f is left continuous, is continuous from left of b. What does it mean, continuous from left of B? Right? So we can apply the definition, which is the limit of the function as x approaching B, f of x, right? Approaching B from smaller than B, okay, from smaller than B, and that equals to f of B. So that's the second case. Okay, that's what it means. And the third case, right? I'm going to just copy and paste and change a couple words. Is continuous on another interval. So this time you can see, well, you will guess it. I'm sure you guessed it, right? Like this, it's half open, but open on the other side, right? So f is continuous for every point inside, is continuous from right of A. Right of A. So approaching A from larger than A, and that is equals to f of A. Okay. And last but not least, okay, last but not least is completely closed interval. Completely closed interval. So not only is continuous every point inside, it's continuous from left of B, it is also continuous from right of A. So we're going to put these two parallel to each other. So these are the interpretation of this definition. This is the interpretation of this definition. Okay, so we got one more example to cover, and that will end this lesson, and we do things next time. Okay, show that we're going to do properties next time. Okay, in a different lesson. We don't want to make this too long. This is already over an hour. Okay. Show that the function is continuous on the interval, closed interval from -1 to +1. Right? So how do we show that? So first we need to show, right, for any A, between +1 and -1. And we're going to observe the limit, right? Because we're going to demonstrate continuity, right? So limit x approaching A, x approaches A, and the function, right? So let me try to get this done sooner so it's not too long. So that's for the limit. Obviously, it is defined, right? The function is defined everywhere. This is a domain. This is a domain. Okay. So to determine domain, let me just insert a little bit of thing before we do the limit. To determine the domain, you just have to take 1 minus x squared, right? That needs to be greater than or equal to 0. And this will lead to x squared less than equals to 1, right? And continue that process, and you take square root on both sides, right? You take square root on both sides. The square root of 1 is still 1. then you get to the absolute value of x is less than equals to 1, right? So our basic algebra, and last but not least, we have decided that the domain is between -1 to +1. That's it, okay? So the function is defined on the entire interval, including -1, +1. So we just follow, right? Because we're going to show this function is continuous on the interval. So the definition is no problem because all of these numbers between -1 for the function, they're defined, right? And let's see what we have. As x approaching a, we can do direct substitution. And those, because each individual limit exists, right? So we can take limits on either one. So we can take limit individually. That's what we're saying. So we use limit law and limit property, right? What do we learn? So we can do direct substitution. So this is a 1 minus direct substitution. So we're going to replace x by a. And this actually equals to f of a, right? So in one stroke, we have demonstrated that this function is continuous, right? F is continuous in the open interval. This is demonstrated. And next, we need to demonstrate, right? On the -1 side, is continuous from right. On the one side, it continues from left. So we're going to consider these two limits. This limit, okay, let me make it smaller. Okay, from -1, but larger than -1. Limit from right, and the other one is limit from left. Right? We just talked about those definitions. So now what do we get? Limit from right of -1, right? So our function is this piece. As x approaching -1 from larger, we can also directly plugging in, right? So this is going to be 1 minus square root we're going to replace x by -1. Limit exists, right? We use limit laws. So this piece is going to be 0, so equals to 1. And is the function at 1 equals to 1? So f of -1 is you plug in, right? You plug in. F of -1, you just plug in -1. It's the same, okay? And secondly, let's look at limit from left on the function at 0.1, right? So this is the 1. Oh, this is going to be negative sign, right? Smaller. Oops. It's also a direct substitution. Okay, direct substitution. We don't really need the parentheses. Substitute by 1. It equals to 1 again. And this equals to f of 1 for sure. So we have demonstrated, even though the steps are pretty trivial, we have demonstrated all three, right? So now we can say the function is continuous on the closed interval. So I'm just going to copy that sentence, right? You can see a lot of cases. I'm doing this is not only because I'm lazy, it's because I want to show you that in a lot of the cases, you really don't need to create your own sentence. You just need to you need to know what sentence to use. You just copy and paste and change a couple of things. Okay, because the best way to demonstrate is by proving the definition applies there. So what is the best way to quote the definition? You quote the definition, okay? So that's all for this lesson that we have introduced quite a lot of material on continuous function, continuity, discontinuity, and the various cases of discontinuity. Thank you for watching.